Thank you very much. Great talk. It's time for questions. Tom?
Thanks for the talk, David. So when you say the sigma, can you go back to the first case where you're just escaping from a well?
Like this one?
Yeah. And where you're bound.
Okay, like here.
You got the two-sided bound, right? So that sigma is that an entropy production? Or an
Yes.
entropy? Yeah. So how does that work? How does that bound approach equilibrium then? Because in equilibrium, the entropy production is 0. So whereas I think in your graph, you showed it approaching equilibrium and it was giving you a non-zero thing.
I mean, okay, so you're saying like here, no?
That picture, right, yeah.
Mm-hmm.
Am I right that gamma going to 0 is approaching equilibrium?
Yes, gamma going to 0 is approaching
So
equilibrium.
that's giving you a non-zero, it's tending towards a non-zero thing, but the entropy production should be 0 in equilibrium for all the time, right?
But here there is also the limit of epsilon in front, so you are closing everything to 0. And this bound here is represented leaving aside the epsilon, let's say. So it should be all rescaled in this sense.
Right. Oh. Okay.
So yeah.
Okay, fine.
Wei Cheng, please.
Hi, thank you for the great talk. A basic question, what's the definition of the escape rate here? And what's the physical meaning of the escape rate?
Okay, so the escape rate is defined according to, let's see if I can, okay, according to the Friedling and Wenzel theory. And so you are actually, because out of equilibrium, you have the quasi-potential playing the role of the potential at equilibrium. And so the escape rate is actually depending exponentially on the barrier height that you have to overcome. So going from the stable fixed point to a saddle, because for us a transition is a path connecting the stable fixed point to a saddle. And to reach the saddle, you have a path, a barrier in quasi-potential that you have to overcome. And so this is basically the definition.
Okay, I see, I can understand it. So what's the physical meaning of this limit? Epsilon times logarithm escape rate.
Oh, so basically you build this chain of inequality here because you have to promote this you have to take down this exponential from here, no? So you are applying the log.
Also, this limit is exactly equal to the large deviation function. Is that correct?
I'm sorry, what?
So this limit is equal to the large deviation function delta I? Is that?
Oh, yeah, it is.
Okay. Okay, thank you.
Thank you.
Okay, so I think we'll thank Davide and all the speakers of this session for very nice talks. And we have slightly less than 15 minutes for a break.
Thank you, Sarah. I'll take over from here, I suppose.
Yeah, I think it's your turn.
Okay. Do I need to be host?
No.
No. Okay.
It's essentially
I'll
everything.
stay as host. I'm Jeremy for today.
Okay. So
And
you'll be manning the Zoom bombing for the second half.
okay, I'll take a short break.
Okay.
结束。
Hi, Wade, do you want to try your slides?
Yeah, just about to. Can you guys see my pointer?
Yeah.
Okay, nice.
Any funky transitions you want to test out or videos?
I don't think so.
All right. Good stuff. Thanks.
How are you doing, Wade?
Yeah, good. How are you?
I'm okay.
Yeah,
But I haven't seen you for a while, so it's good to know.
been many years since in person, certainly. Yeah.
Yeah.
Is Evan Peepoff here? Just looking ahead to all of our speakers to see if they're actually in the audience. No Evan so far, okay? Okay, I think we're on time now, so we're going to get started. So if you're out and about, come on back to the screen now. So I'm David Savak. I'm going to be the chair for this second session of the day. And so we'll have 3 lightning talks of 15 minutes, 12 minutes, and 3 minutes of questions. And then we'll have 2 longer half-hour invited talks. So with that, I'll hand it over to the first speaker, Wade Hodson. Please, Wade, the floor is yours.
Great. Yeah, thanks, David. Today I'm going to be talking about a project I've been working on with Aljaž Godek in Göttingen on thermophoresis of a particle via coarse graining of an explicit non-equilibrium medium. So the talk will be very straightforward. I'll give a brief introduction to thermophoresis, I'll describe our model, and then I'll talk about some of our results. So the first question is, what is thermophoresis? Thermophoresis refers to particle flow in response to a thermal gradient. So if you place some colloidal particles in some medium with a temperature gradient, not only will they exhibit random Brownian motion, but they'll exhibit a directed systematic drift. If it's towards the cold side, then that's referred to as positive thermophoresis. If it's towards the hot side, it's referred to as negative thermophoresis. And so the simplest sort of phenomenological description for this phenomenon is in terms of if you assume the particle flux at any given point is just expressed as a sum of 2 terms, so a normal diffusive term with a diffusion coefficient d, and then a thermal diffusion term proportional to the temperature gradient with some thermal diffusion coefficient d sub t. So the rest of this talk is going to be theoretical, but I should very briefly mention some examples and applications of thermophoresis. So I don't have time to go into any detail on these, but one particularly important one is particle manipulation and sorting or filtering, because essentially different particles, different species, different isotopes, and so on have different thermophoretic properties, so they'll be affected differently by a given thermal gradient. So this can allow us to sort particles. So the second question would be, what causes thermophoresis? So thinking here in particular about colloidal thermophoresis, so a colloidal particle embedded in some solvent medium, solvent particles typically much smaller than the colloid. There are many mechanisms which can give rise to thermophoresis of the colloidal particle. I don't really have time to talk about any of them in detail, but what I can say is that there are a couple theoretical tools that are commonly used for treating these sorts of systems. So first of all, we have the general framework of non-equilibrium thermodynamics, which I sort of alluded to on the previous slide. So we have some particle flux with some diffusive component and then some thermal drift component. And so in this framework, the question becomes, okay, given some sort of lower level model, how do we evaluate what this thermal diffusion coefficient is? And one approach is sort of equilibrium or quasi-equilibrium type theories. And the idea here is to evaluate this coefficient, or at least the ratio of that coefficient and the regular diffusion coefficient, by looking at what the steady state of a colloidal system is when this diffusive flux and this thermodiffusive flux balance, and then assuming that this non-equilibrium steady state has some equilibrium type properties. Another approach is with hydrodynamic models, which is basically where you assume that the solvent surrounding the colloid can be treated as just a continuum, and then evolving according to Navier-Stokes equations. So our model is sort of complementary to these approaches in the sense that, we're taking a very sort of minimal level of description. We're not trying to, in detail model the mechanism behind any particular colloidal system. But what we're trying to do is sort of go a little bit deeper than the thermodynamic or hydrodynamic description and start from a particle-based model of a tracer particle plus some non-equilibrium medium. And so in this model, which I'll describe in a minute, we want to evaluate the Serre coefficient, so the ratio of these 2 diffusion coefficients, which is going to characterize the strength of this thermal drift. And in particular, we're going to be interested in the conditions under which this coefficient can switch signs. So we can move from the particle being attracted to the cold or to be attracted towards the hot. So here's a schematic of our model. I've drawn it in 1 dimension, but we've done this for higher dimensions as well. It consists of three pieces. First of all, these green balls connected by springs represent the medium or the solvent. So this is just a lattice of coupled harmonic oscillators. Second, we couple this medium to this tracer, this yellow ball here, via some interaction potential U. We'll take this interaction potential to be spherically symmetric, short range, and also smooth, but otherwise fairly general. And finally, in order to introduce the temperature gradient, we couple each of these medium particles to their own thermal bath given by these squares here. And so we can make these thermal baths at different temperatures to impose any temperature profile that we choose. So specifically, here are the equations of motion. They're Newton's laws for the tracer and also for the medium. So here and here, we have the interaction between the medium particles, each of the medium particles and the tracer. Here we have the spring constants that couple the medium particles together, and also, there's also sort of an on-site pinning that couples each one to a site. And then finally, we have damping and noise coming from each of the thermal baths interacting with each of the medium particles. And so the important thing to notice here is that the TI, the temperature experienced by each medium particle, is actually a function of the position of the medium particle as dictated by whatever temperature profile we decide to impose. And so this is going to be important because when the tracer interacts with the medium, it's going to actually push the medium particles out of the way and cause them to experience a modified temperature from what they would in its absence. So starting from this model, our method is first of all to make a Markovian approximation. So we assume that the dynamics of the tracer are much faster than the medium. So that allows us to coarse grain over the medium and end up with a Langevin description for the tracer alone, which is given here. To evaluate the terms in this Langevin equation, we go on to make a small noise or low temperature approximation. So we assume that the medium exhibits small, approximately Gaussian fluctuations about its mechanical equilibrium positions. Then to go further, we take a continuum limit. So we assume the lattice spacing of the medium is very small. And finally, we take an overdamped limit of the tracer and end up with a coarse grain description with these diffusion and thermal diffusion coefficients evaluated in terms of the original microscopic model. And so here are the results in their generality. So again, we can do this in 1, 2, or 3 dimensions. We have this Smolakowski equation for the tracer distribution in its position space. And we find first the diffusion coefficient depends on this local fluctuation dissipation relation, which relates it to the local temperature at the tracer position X, and this damping rate gamma for the tracer, which is defined down here. Second, this Serre coefficient, which is the ratio of this thermal diffusion coefficient to the regular diffusion coefficient, is given by 1 over the local temperature plus 1 plus this alpha quantity. And so this alpha and this gamma here, they're defined in terms of these special functions, which I can flip to on some backup slides if we have time at the end. But just note that they depend on the derivatives of the interaction potential and also the coupling strength within the lattice. And the important thing to notice here is that this alpha can have a positive or a negative sign, which means that potentially we can switch from having positive thermophoresis movement towards the cold to negative thermophoresis movement towards the hot, depending on the model parameters. In particular, we can see this in the steady state. So if we set the current here equal to 0 and look at the steady state probability density, if we look, for example, in 1 dimension with a linear temperature profile, what we see is that for different values of alpha, if alpha plus 1 is bigger than 0, then at higher temperatures, we're less likely to see the particle. So this is positive thermophoresis. And we get the reverse if alpha plus 1 is less than 0. Also, we can go into more specifics if we look at the weak coupling regime. So here I expand those previous results to second order in the interaction potential. We get in particular, we get a simplified expression for this alpha. It factorizes into 2 factors. First of all, this integral over the curvature of the interaction potential, the squared curvature. And second of all, this Q function, which depends on, it's basically an integral over the modes of the lattice. And in particular, for different dimensions D, this Q is negative if D is equal to 1, but positive otherwise. And so negative thermophoresis in this case, in this weak coupling regime, is only possible in one dimension. And we also have this simplified expression for the damping coefficient. Going back to the general case of strong coupling, but then considering a particular interaction potential, we can again evaluate the Serre coefficient. So here I've chosen an interaction potential where I basically stitch together two quadratic functions in the radial coordinate with some characteristic energy E0. So E0 can be positive or negative. If it's positive, it's repulsive. If it's negative, it's attractive. And we also have some interaction length sigma. And in this case, if we find that if the medium particles, we assume there's no coupling between adjacent medium particles, we get this simplified expression for the Serre coefficient that depends on this function W sub D, which is a function of this dimensionless interaction strength. And so I've plotted this here as a function of eta, the dimensionless interaction strength, for a couple different dimensions, you know, the normal ones, 1, 2, and 3. And then what we find is looking at dimension D equals 3, we see that for sufficiently negative eta, so when we have a strong attractive coupling, this W can actually become negative, and therefore it's possible to then get a negative Serre coefficient. So for sufficiently strong attractive coupling. So to summarize, starting from this particle-based description, we derived a Langevin equation for a tracer in a non-equilibrium medium. We obtained expressions for these transport coefficients. And finally, for a particular case of medium tracer interaction, at strong coupling, we saw this switch from negative to positive thermophoresis. And there's still a lot of stuff to do in the future. We want to compare with numerical simulations, also with existing theory. We'd like to look at different tracer medium potentials. And also there's this case that I didn't really discuss, which is the case of no on-site pinning for the medium. So the medium is free except for its interaction with the potential and the nearest neighbor couplings. Yeah, so that's about it. Yeah, thanks for your attention and happy to take any questions.